pull my chat up. So I got my chat open. Great. Okay. And I don't know why the lighting is so bad in today, but I don't know. I don't seem to be able to make it better. So there was a request to revisit this problem from the other day. Totally happy to do that. Happy to do whatever you all want to do today. But let's get started with this one. So the trick to this is mostly that it looks terrible. So I'm hoping for a U substitution. And kind of the trick to finding that U substitution is recognizing that 1 over e to the x is the same as e to the negative x if I bring it up on top. So I would rewrite this to say e to the negative x on top, and then e to the negative x plus 3 on the bottom. Because now, if I let the entire denominator be equal to u, then du is negative e to the negative x. Which I almost have, I just don't have that negative sign. So when we do the u substitution, putting that back in, all of that stuff on the top, the e to the negative x and the dx, that whole thing becomes negative du. So I've got negative du, the whole denominator was u. And then if we want, we can treat that as saying negative 1 over u du. And go, oh, hey, I know whose derivative that is. That's the derivative of natural log. So I've got negative natural log e to the negative x plus 3 plus a constant. And we can't do much with this. If you really wanted to, you could take that negative sign that's out in front, bring it in as an exponent, but I wouldn't, I just leave it like that. Good times. Okay, so thoughts on what we do today. We can do some more practice with area stuff. We can look at specific problems from the homework. If there are specific homework questions that people have, I'm open. I can make up area problems. Any thoughts on what we would like more practice with today? Okay. Yeah, like between two graphs.
Yes.
I did notice on the homework, and I don't know whether anyone has asked him if this would be true on the test, he gave us pictures for all of them. And so that's kind of game changing. So I don't know, has anyone asked whether he's going to give the pictures? Okay, there is a request in the chat, and on Friday I did do some where we figured out who was on the top and the bottom without having to draw the picture. That's always my go-to because I never trust that we're going to get the pictures for the test. Yeah, so let's go ahead and do some area practice. And I'm going to make some up, but I'm also totally happy to work through any of the ones from the homework. But let's find the area of the region. Bounded by y equals e to the x, y equals 1 minus x squared, x equals -1, and x equals +1. Okay. With or without a picture? So if we're going without a picture, and I'm totally fine with the without a picture. Now, I want to point out a couple things. One, we've already been given that x equals -1 and x equals 1. So partial credit wise, I'm already thinking, oh, cool. I know the upper and lower bounds. And maybe my pen's dead. Ooh, come on. Okay. I know the upper and lower bounds are going to be -1 and 1. So in terms of my integral, I just got to figure out who's on top, who's on the bottom, and throw in a dx. So if I'm going to do this without a picture, I'm going to come off to the side and think about, okay, whatever is going on, it's happening between -1 and +1. What's a nice number we can plug in between -1 and +1? Yeah. So I'm going to pick 0. So I need to know which of my two functions has a larger y value at 0. So I've got e to the 0. Oh, dang it. We got a problem. I thought I was being clever. I was not being clever. We got a problem. What's e to the 0? What's 1 minus 0? So that means I accidentally picked something where my graphs intersect at 0. So I'm going to fix it. I'm going to change my functions because I really don't think this would happen in your problem. So I'm going to switch this. It's not going to say 1 minus x squared. I'm just going to write it backwards. We're going to make this x squared minus 1. Go fix it in your notes. Fix it. I'd say I'd edit that out of the video later, but I know I won't remember to. So, okay, try that again. Cool, now when I plug in 0, I would have 0 squared minus 1, and I would get -1. So that tells me that the parabola has a smaller y value. So the parabola is on the bottom, the exponential is on the top. This would go from -1 to +1, and I'd have e to the x minus the whole equation for the parabola. Before I integrate, I'm going to want to distribute that minus sign through to have e to the x minus x squared plus 1. Don't try to like simplify your final answer, but go ahead and integrate that and then plug in your bounds. And I'll give you all a minute or two to do that. Do we one more time? Should we go over it? Okay. So I've got this thing. I've got my definite integral notation, which is saying this stuff inside is somebody's derivative. Find that antiderivative, plug in the endpoints. So step one, I'm going to find the antiderivative, and we'll go piece by piece. So the antiderivative for e to the x is e to the x. Antiderivative for negative x squared, it's going to be 1/3 x cubed. And the antiderivative for 1 would be x. The next piece is that I'll evaluate this at our endpoints. We're always going to do that top piece minus the bottom piece. So when I plug in 1, I'll have e to the 1 minus, I can do 1 cubed in my head. That'll be 1. So I'll just have 1/3 plus 1. And that whole thing, I'm now subtracting off e to the negative 1. I'll be careful here. Negative 1 cubed is a negative. But then I've got that minus sign there. So that'll be a plus 1/3 and then minus 1. We could distribute the minus sign through, or we could leave it. I'm going to leave it and walk away. I'm going to say that's my answer. Mostly because there's nothing I'm going to be able to do with the e's. So I'm going to leave it here. Would anyone like to see what I would have done if it really was the other problem before I made a mistake and tried to fix it? Okay. I don't know that I'm going to work it all the way out, but here's what I would have done if it was that other one. So originally I had e to the x and 1 minus x squared, negative 1 and 1. Okay. I'm a fan of the fake graph. So I'm going to draw my fake graph. And if I had drawn the fake graph, honestly, this is what I would have done. I would have gone e to the x. It looks something like this. That's a parabola. It points down. That's going to look something like this. Oops. And there's my fake graph. The problem is I can't actually normally solve something that looks like setting these two things equal to each other. It's actually called a transcendental equation, but we don't need to know that. We just need to know that trying to solve that ain't going to happen. So the problem with my fake picture is that I don't actually know where x equals negative 1 and x equals positive 1 go. So I still probably would have gone, oh, it's negative 1, positive 1, plug in x equals 0. Oh, wait, they intersect at x equals 0? I guess I got to fix my graph a little bit. So if I got slightly, well, option one, I'm going to go, well, one of these 2 points has to be x equals 0. Because those are the places where it intersects. So either that's x equals 0 or that's x equals 0. If that's x equals 0, then when I plug something bigger than 0 in, the exponential should be on top and the parabola should be on the bottom. But if that's 0 and I plug something bigger than 0 in, then the parabola would be on top. So I might see what happens when x equals 1. And when x equals 1, I'd have e to the 1 or 0, the exponentials on top. So that tells me this had to be the x equals 0 point. So x equals -1 is somewhere over here, and x equals +1 is somewhere over here. And I would have to break this apart into two separate pieces. So from -1 to 0, the parabola would be on top. And from 0 to 1, my exponential would be on top. I don't think you're going to have to worry about something like that for two reasons. One, I just don't think you're going to be given two functions that you can't solve algebraically unless you are given the picture. So I think you're either going to get the picture or be able to solve it with algebra. And since in this case, I made a mistake because I gave us something we couldn't solve with algebra, and I also didn't give us the picture. So I don't really want to finish this one off. Let's do one that we can solve with algebra so that we can decide if we want to use a picture or not. So more fun. I'm gonna keep this one fairly straightforward. And then we'll do a slightly messier one. So I'm going to find the area of the region bound by y equals x cubed and y equals x. I can do this with a fake graph, or I can do this with algebra. I'm going to go algebra first. So in terms of algebra, I need to figure out where these two intersect each other. So I'm setting those equal to each other. I've got x cubed is equal to x. Tempting to divide both sides by 0 right now, but then we lose information. So from an algebra perspective, we really want to make sure to get a 0 somewhere first and then hope it factors. I would choose to move everything to the left because I don't like factoring with a negative in front of my first term. I know it's dumb, but it's just how I feel. Now I'm thinking about what can I pull out of all of that? Well, these have an x in common. If I pull an x out, I'm left with x squared minus 1. Told you I was keeping it simple. And that x squared minus 1 factors further as x minus 1, x plus 1. So already I know life's a little more complicated because these functions cross each other at -1 and at 0 and at +1. So I have two regions to figure out who's on top and who's on the bottom. And I'm going to make the case that personally, I'm less likely to make a mistake with my fake graph than I am to make a mistake plugging in decimals or fractions. Totally up to you. If you love the fractions or decimals, you could plug numbers in here. I'm going to go a slightly different route and say, yeah, let's go fake graph. Y equals x cubed. We know what that looks like. We ought to know that y equals x cubed kind of squiggles like this. And y equals x is a line with a positive slope. So if these are going to intersect 3 times, that line has to do something like this so that they intersect 3 times. So in this region between -1 and 0, the cubic is on top. We've got an x cubed on top and the x is on the bottom. But over here, between 0 and 1, the line is on the top and the x cubed is on the bottom. Which means that when we go to write this as an integral, we have two separate pieces. I have to integrate from -1 to 0, putting the cubic on the top. And I have to integrate from 0 to 1, putting the line on the top. I think it's good practice to actually find those antiderivatives. So I'm going to let you find those antiderivatives and then plug in your endpoints. And the numbers will work out nicely. So, well, nice enough. You're plugging in ones and zeros. We're going to be okay. I don't. And I'm processing. Mm-hmm. So each one of those, like in each region, it should be the top function minus the bottom function. So the problem, and the picture looks almost like this. So the cubic is on top over here, but the line is on top over here. So we have to break it into two pieces so that we've got the right top minus bottom in each piece. And I would say for all of the problems in the home, well, for all the problems on homework 12, he definitely gave us a picture so we can use the picture to see who's on top and who's on the bottom. I also think that even if he didn't give you the picture, it would be things that you should probably be able to graph, at least to a fake graph like I did, right? So parabolas and lines, totally fair game for him to expect that you could graph on your own. So if we go through finishing this off, for my first piece here, I'm going to end up with 1/4 x to the 4th minus 1/2 x squared, evaluated, from -1 to 0. And then kind of the opposite, so 1/2 x squared minus 1/4 x to the 4th. And that's evaluated from 0 to 1. Well, if I plug in 0, and be careful about the order here, we're always plugging in the top thing first. So I'm going to plug in the 0, and I'm going to get 0 everywhere when I plug in 0. But that means it's 0 minus, and then what I get from plugging in the -1. So 1/4 times -1 to the 4th minus 1/2 times -1 squared plus, here when I plug in the 1, I'm just going to do the math right away because I'm plugging in 1. So, oh, no, I guess I need like giant parentheses over there. So if I plug in the 1, I'm going to end up with 1/2 minus 1/4. And then when I plug in the 0, I'd have minus 0. If I were to go through and clean this up, -1 to the 4th leaves me with a positive. -1 squared also gives me a positive. So I've got like minus, and then in parentheses here, I'd have 1/4 minus 1/2 plus, and then over here, I can get rid of those parentheses. I can distribute my minus sign through, so -1/4 plus 1/2 plus 1/2 minus 1/4. 1/2 and 1/2 is 1. 1 minus 2/4 gives me a positive 1/2. I don't think you have to get it down to like nice final answer. I think you probably could have quit here, but it did simplify nicely. Leaving it up for a second in case there are questions about this one. Then I'm going to make up another one. I'm going to make up one that is ever so slightly ugly. Since I feel like he's been giving us pictures, I'm going to do one where I'm going to give you the picture, but it's still going to be a little bit messy. So that is y equals x squared. That is y equals 4 minus 3x. I'll give you, no, I'm not going to give you the intersection point. You can find it. It won't be bad. But the area that I want to find is the area in here. Together, or you all want me to give you a minute? Okay, I'm going to let you try. I will give you a hint that we can at least talk through this first part. Since my area needs to be a function, needs to be a top function minus a bottom function, you can imagine that this down here is, I was going to like test my artistic abilities here. Okay, so you can imagine that this little place down here, it's a little room, and I'm going to shrink myself and put myself inside of the little room. Give myself glasses. Okay, that's me. I'm tiny. I'm standing inside of the room. When I'm right here and I look up at the ceiling, what function tells me the ceiling when I'm standing right there? Yeah, it's going to be the x squared. But if I take a little walk over here, okay, and I stand over here in my room and I look up, there's a different function for my roof. That tells me that I have to have two separate integrals. So I'm gonna have to break this apart here and separately figure out what's the area of that first room with a top minus a bottom. plus what's the area of my second room with a top minus a bottom. I'm going to let everybody sit with that. So you have a couple things to figure out. You'll have to figure out what the limits of integration are and figure out who's on the top, who's on the bottom. My clock says 12:42. I'm going to give everybody a solid 3 minutes to play with this. I'm actually setting a timer. Doesn't mean you have to get all the way done in 3 minutes, but I really want you to dig into it for at least 3 minutes. So do you all want more time? Hit our 3 minutes. No votes from Zoom. The room's going to get to call it. Great. Let's do it together. So I don't know where to start, but I think I'm going to start with my functions. There's a secret function at the bottom of both of these because the x-axis is secretly y equals 0. So technically these are both something minus 0. You could also leave that off. You could leave off the minus 0. That's why we weren't bothering with it before when we were just finding area under a curve. Because whenever I draw an area, and we're talking about the area like between that curve and the x-axis, technically that bottom was always 0. Okay. On the left-hand room, my ceiling is given by x squared. In the right-hand room, my ceiling is given by 4 minus 3x. Now I got to do the limits of integration. Well, the first one I know is that the 0. Cool. That's it. That's the one I can get by just looking at the graph. The rest of them I'm going to have to work for. So I'm going to go ahead and find the intersection point of these two curves. So if I set them equal to each other and I have x squared is equal to 4 minus 3x, I would move everything to the left-hand side because I like my x squared term to be positive to factor. And I think I did it right. And this is going to factor as x plus 4 times x minus 1, which gives me two numbers, but I'm only using one of them. If I were to continue drawing this parabola out, it's going to intersect somewhere over here with a negative x value. But based on the picture we've got, this must be the positive 1. So I know in that first region, I'm going from 0 to 1. And in the second region, I'm going from 1 to something else. Now the extra piece of the something else is I need to figure out essentially the x-intercept of this curve. So I'm going to take the y equals 4 minus 3x and set that whole thing equal to 0. And I'm going to get that x is equal to 4/3. So the second one, I'm integrating from 1 to 4/3. I'm going to go ahead and finish it because I think it's not terrible. When I come in here to integrate, the integral of x squared is going to be 1/3 x cubed. I don't have to deal with the 0, and this is going from 0 to 1. I'm adding that to what we get over here. And over here, when I integrate, I end up with 4x minus 3/2 x squared from 1 to 4/3. Now there's a question in the chat about where my y equals 0 came from. And y equals 0 is secretly the forgotten equation for the x-axis. If I needed something on the y-axis, that y-axis is secretly x equals 0. I think we like talk about it for half a minute in algebra 2, and then it's just gone. But secretly the equation of the x-axis is y equals 0. So when we need an equation to put in there, that's what we get. Okay, to finish this one off, if I plug in the 1, I've got 1/3. If I plug in the 0, I get 0. This one, when I plug in 4/3, I'll have 4 times 4/3 minus 3/2 of 4/3 squared. And then minus plugging in 1, which would give me 4 minus 3/2. I'm going to quit while I'm mostly ahead. So to kind of re-look at my picture, but maybe without the messiness of my little tiny people standing in there. We've got a line, and that line is y equals 4 minus 3x. Here's my x-axis, here's my y-axis. And then we had part of a parabola that's y equals x squared. So I had to break this into two separate regions. And for this first region, my lower bound is 0, but my upper bound, I had to get from whatever that intersection point is. So I'm just going to call that intersection point like x equals a. So I know this first one had to go from 0 to a. For the next part, I can see that we have to end over here, which means I need to know where our line crosses the x-axis. So I needed to find the x-intercept of that line, which I got by doing 0 is equal to 4 minus 3x. So that's where my 4/3 came from for this second integral that went from a to 4/3. And then got to find the intersection point for that piece of it. Okay, we got 8 minutes left. What's next? Am I making up more? 100%. You can leave off the 0. You do not have to write it in there. Yeah. Okay. I'm going to give us one more. Okay, I decided to throw some trig in there for fun because everybody loves trig, I know. So if I'm trying to find this area, well, the good news is I've been given some x bounds. Bad news is I still have to figure out who's on top and who's on the bottom, unless he's going to give us a graph, which honestly, I really think he's going to give you a picture. But if he didn't give us a picture, these are both functions we should be able to graph. Also, these are values that we should be able to plug in and get something for. But I'm going to show you method of last resort. I don't know what the graph looks like. I don't know how to plug stuff in. Pick something to put on top and roll with it. And let's see what happens. Anyone have a gut instinct of which one of these is going to be on top? Cool. I'll just say the cosine is first. So let's see what happens. So method of last resort. Don't get paralyzed. Right? You don't have time to sit there and panic about which one is on top. Just pick one, just pick an order and go with it. So I'm going to do cosine of x minus cosine of 2x from 0 to pi over 4. And just see what happens. Well, if I integrate cosine, I get sine of x. When we integrate cosine of 2x, we get almost that, but we end up with that 1/2. So I'm going to have 1/2 sine of 2x. And you can always check yourself by taking the derivative to make sure you get back to where we started. And then I'm taking this from 0 to pi over 4. Well, when I plug in pi over 4, I get sine of pi over 4 minus 1/2 sine of, and 2 times pi over 4 would make that pi over 2. So I'm going to have like that whole thing minus sine of 0 minus 1/2 sine of 0. Well, sine of pi over 4, I think about it as 1 over square root of 2, but most people do square root of 2 over 2, so I'll go with that. Minus sine of pi over 2 is equal to 1. So that would be minus 1/2. Sine of 0 is equal to 0. And that's going to be some more 0. Well, I actually happen to know now that we did it right. Because the square root of 2 is bigger than 1, so the number that we just got is positive. But if you get a negative number when you're done, overall number, then you switch the order. And just from a really practical standpoint, if you were taking a quiz or an exam and you had worked through a whole problem and got a negative answer, I would just write a note to the TA. I would write out in words, I know this should have come out to be positive. I switched the order of integration. I don't have time to go back and redo it. My guess is or in my experience, writing out the how you caught your mistake and just saying that you don't have time to go back and redo it, but you're telling them what you would go back and do, most of the time, you'll only lose a point. If you work through it correctly, but like in the backwards order, and you catch it and you write it out there, you're not going to lose points, or not a lot of points. I'm out of time. I do have Zoom office hours from 2 to 3 today. So if there are any particular questions from the homework, or if you want to work back through any of these, or you want me to make up another dozen practice problems, you are totally welcome on my Zoom office hours later.